Today I'm here to present the company and our research we did in SAF Tehnika. So what we are doing, we are a company designing and manufacturing in-house electronic products. And we have three main product lines. One is microwave radios, point-to-point radios, then handheld spectrometers, which basically are used to set up the point-to-point radio links. And the third one is a vertically integrated IoT ecosystem using our own proprietary protocol. And this is, of course, the reason why I'm here today. And we are selling these products around the world. Here you can see the red color represents the countries we are present, and we have 4 offices. The main one, all the research and manufacturing is in Riga, since approximately half of the business is in North America. So we have an office in Denver, Colorado, and we have also sales offices in Bogota and Singapore. But let's go back to Riga, because my talk today is about Riga. This is a picture how the Riga looks like. And we were invited by Riga Technical University, which is in the front of this picture. And they came up with a project when they wanted to have a real-life data set in order to improve their machine learning algorithms. So they needed sensors which are generating these data, and we were as a partner in order to supply these sensors. This is a good thing to supply sensors, but it's not very fun. It's not interesting from the research point of view. So we wanted to make something fun, something interesting for us, for our R&D. So we were thinking what to do, and our thinking and motivation was like that we know as a radio experts, we know that there is some level of the radio which can be present when all these messages interact so that the system stops working. And of course, this is correct at one situation, and we were thinking how to address that. We have heard about the mioty, which looks really good on paper, and we were interested to see how it behaves in real life, to have experimental proof, so to speak, that this is good. Because since I am not attending this mioty summits, this is my first time actually, so I don't have this information, and I'm not able actually to find a written experimental data of the substantial mioty deployments, and I'm interested to have them, because for me as a company, it's not enough to have a qualitative proof that it is existent, that it's working, and that it's better. In order to make decisions to invest in one or another technology, we prefer to have a quantitative proof. Since we were not able to find such a description, so we decided to make it ourselves. And we were comparing basically our existing protocol with mioty. Something which we have with something we would like to have. Probably you recognize the characteristic mioty pattern here. And these 3 rectangles describe how our protocol looks in the frequency scale. And you can notice that we have 3 channels, and each base station has its own channel, and all the sensors connected to the base station always works in the same channel. It's predefined, and you can see that one channel overlaps with mioty, EU1 frequency plan, but other 2 are slightly away from that one. This is a technologies I want to compare, and in order to do this really in a proper way, I need hardware. And for hardware, we were using our best-selling product. This is basically CO2 sensor, which also measures air temperature, relative humidity, and atmospheric pressure. Therefore, the name Aranet 4 metrics, and we are selling this in hundreds of thousands, large quantities, our best-selling product. But today, probably we are more interested in radio properties. And luckily, this product already we're using the radio chip, which is compatible both with our protocol and mioty. So we can use exactly the same hardware to do really apple-to-apple like comparison. And in order to make this experiment as close apples to apples as possible, so we use, of course, the same power setting, which is maximum allowed in Europe. We choose transmission interval 2 minutes, and I have to tell that these are, in both cases, Z-class devices, only transmitting devices. Okay, I have hardware, I have idea, now I have to execute it in real life. So the task from the university is to equip all the campus with these sensors, so that in every room, like literally every room, there is one CO2 sensor. But for my apple-to-apple comparison, I need buildings which are similar. Otherwise, I cannot make this real-life test. And of course, when I look closely on this map, I notice these two buildings, which are now in different color, which looks similar. So this is a good candidate for two technology comparison. And if I look closer to them, then indeed, not only the shape and the configuration of them, but also the internal structure is very similar. And this is actually a dormitory. So this is very suitable for my experiment. And it's also possible to put the base stations in a symmetric manner, which is important, of course. And then I put a sensor in every room. So this is my setup. Looks like really similar. And luckily, there's number of floors, which also something I like to have. And 8 of them are identical, which is again good for me, good for my experiment. So I equip one part of the building with mioty sensors, with the frequency plan EU1, and another one with Aranet. For Aranet, I must have one base station in each floor. And for mioty, I pretend that I don't know anything about mioty. From the end user perspective, I also put 8 base stations. The principal difference between these two is that for Aranet, base station in one floor can hear only the sensors in that particular floor. Whereas for mioty, as you know, it's possible to configure so that every base station hears all the sensors. So this is the main difference we should take into account when analyzing results. At the end, I'm happy with my setup. I'm saying that it's really a good real-life lab, so to speak, to compare these two technologies. So I have close to 500 of one technology and close to 500 of another technology. In order to give you some insight in our analysis, I choose this graph where I have signal strength versus packet loss. Each dot represents one particular physical sensor, and this is the average value over the 24 hours. And these results you're already seeing is the Aranet channel 3, which is the most distant from mioty. And this is something what I expect from Aranet, actually. This is in good circumstances, I have 1 or 2% packet loss, but in average at this sensor density, I typically have 7-8% packet loss. I consider it normal. The same for the channel 2. Very similar picture, and also something I expect. Things are becoming interesting when I look at the channel 1, which, if you remember, is the one which overlaps with mioty. And we did a series of experiments to prove that it's really mioty which influences our protocol in this manner. So packet loss is increased approximately 2 times. While mioty itself, it's almost like not affected in any way in these circumstances. You see all these almost 500 dots you cannot distinguish them. They are all in the left-hand side. The packet loss is very, very close to 0. And in this graph, it actually doesn't carry much information about mioty because it's just a line. Therefore, I choose to redraw the picture in a bit different manner, so I add some more information. This graph here is still RSSI versus packet loss, the same we had in the previous picture, but in addition, I put the distribution density function, so I see how many sensors I have at each strength. Since the setup is static, so it represents basically number of sensors. And I remind you that at this point, I have all 8 base stations turned on. And then I'm thinking that this is a pure monitoring system, Z-class system. Who needs 0.056%? I think it's overkill. So it's a really room for improvement or optimization. And I'm starting to cut off these nice mioty base stations to see is there any limit to mioty. And I turn off every second base station. And you see the picture is not influenced seriously. Of course, there is some increase in packet loss, but it's not significant. And I continue. I leave only 2 base stations turned on. And now I see really some increase. I have a packet loss of 1.1%. And what is characteristic in this picture, I want to draw your attention that you see that there's approximately the same number above and below 100 dBms. But packet loss is much higher for those where the signal is weaker. Therefore, I speculate that the dominating packet loss mechanism is not interference of the packets, but it's just attenuation of a radio signal. And of course, I can go further. I can keep just to one base station. And now I'm really in a Aranet-like situation, so I have 6%. And yeah, but it's still very good actually. For practical applications, it's very good. 6% lost if you have measurement every 2 minutes. It's a very good result. So far, so good. Life looks like chocolate, right? But what I have learned in life is that for free, there is only cheese, right? Appears that this is the case also. So there is another, actually, from the end user perspective, very important parameter, which is battery life. And you can see that for Aranet, we expect 2 years with these settings, but exactly the same device working in mioty in this frequency plan has only 10 months. So this is a price I have to pay. And after this information, me as a project manager, I have to choose how to proceed, what technology to use for the whole campus. And since this is a research project, and since we are members of mioty Alliance, of course it's a mioty. So we equipped all the university campus with mioty sensors. And right now there is 2,726 mioty sensors working there. The project is ongoing. There are a lot of other experiments, but I cannot squeeze them in 15 minutes today. But these data are used on an everyday basis by the university staff, and also researchers are using this data set to adjust their machine learning algorithms. But I have to conclude my presentation, and main takeaways which follows from the data I shared with you is that mioty provides orders of magnitude smaller packet loss. That was what was expected, but now I have it quantified. Even more interestingly, the mioty cluster influenced Aranet while remained intact itself. So this is a very important result. And we say that in this situation, when you have buildings with a lot of reflections, signal attenuation, then the mioty technology, although it's really beautifully designed, it still cannot cheat the fundamental physics. So signal attenuation is there and dominates mechanism in buildings. Battery life is a thing which has to be sacrificed. And thank you for your attention.